As data pulses through a fiber optic network, it moves at speeds and in formats optimized for hardware, creating a fundamental gap between machine protocols and human language. Computers and networked devices do not recognize names. They identify one another using precise numerical strings known as IP addresses. This numerical format allows routers to determine the most efficient path for data to travel across the global infrastructure. Humans, by contrast, are optimized to remember labels and names rather than long, abstract sequences of digits. With millions of active websites currently hosted on the internet, memorizing the specific IP address for every destination is a cognitive impossibility for the average user. To make the network usable, engineers developed a translation layer that bridges this gap between human-readable names and machine-routable numbers. That translation layer is the Domain Name System, or DNS. Its specific role is to resolve a domain name into the corresponding IP address required to initiate a connection. It works like a phone book. Provide the name, get the number. The name is a user-friendly handle, while the number is the hardware's actual destination. Without this translation, browsers lack the numerical routing data to locate the server. To understand how this works at scale, we must look at the specific sequence of delegation that allows the system to find a single address among billions without a centralized master list. The entire process begins the exact moment you type a domain like yahoo.com into a browser and hit enter. First, the operating system checks its local cache memory to see if it has connected to this address recently and already knows the IP. If no local record exists, the computer must send a formal query out to the network. As the packet moves, the query travels to the resolver, a server typically managed by your internet service provider. The resolver acts as a dedicated agent for your computer, taking on the task of locating the IP address across the global DNS hierarchy. Like the computer, the resolver checks its own internal cache first to see if another user on the same ISP has recently requested the same site. If the resolver doesn't have the answer stored locally, it begins the process of querying the global tiers of the DNS system. When the resolver needs to start a fresh search, it goes to the very top of the architecture. These are the root servers. They sit at the apex of the DNS hierarchy, and their locations are distributed globally to ensure the system remains reachable. There are 13 sets of these root server clusters, each identified by its own unique IP address. To ensure security and redundancy, these clusters are operated by 12 independent organizations, preventing any single entity from controlling the entire root zone. A common misconception is that these servers hold every IP address on the internet. In reality, they don't know the IP for yahoo.com. Instead, the root server reads the domain extension, the .com at the end, and directs the resolver to the next level of management. It acts as a primary director, ensuring the query is sent to the correct regional authority for that specific type of domain. The resolver now queries the top-level domain, or TLD server. TLD servers manage the records for broad categories like .com, .net, or .org. Because our request is for a .com address, the resolver specifically contacts the TLD server responsible for the .com registry. Even at this level, the TLD server still does not provide the final IP address. It instead identifies the specific authoritative name server that belongs to the organization owning the domain. The TLD tier effectively narrows the search from the entire internet down to the specific name servers controlled by the website's owner. Finally, the resolver reaches the authoritative name server. This server is the final, definitive source for all records related to that specific domain name. Because the domain owner maintains this server, it holds the actual current IP address for the web server hosting the content. The authoritative name server responds to the resolver with the exact numerical address for yahoo.com. This concludes the chain of delegation that began at the root. The resolver has successfully translated a linguistic name into the mathematical format the browser needs to proceed. As the IP address travels back, the resolver performs a critical task. It saves the address to its cache. This allows the DNS system to scale. By storing the result, the resolver doesn't have to repeat the root to TLD to authoritative sequence for subsequent requests. If another user on the same ISP requests the same domain minutes later, the resolver provides the IP address instantly from its own memory. This localized storage prevents the higher-tier servers from being flooded with redundant queries for popular websites. This distributed caching mechanism is the specific tool that prevents massive network-wide bottlenecks from crashing the system during peak traffic. In the final step, the resolver delivers the numerical IP address back to your computer. Now that your computer has the correct IP, the DNS process is over. The browser establishes a direct connection to the target web server. The computer uses that numerical address to route a request for the specific web page files it needs to display. This entire multi-tiered search, traversing the globe to find a single specific record, happens in just a few hundred milliseconds. The complexity of the global hierarchy is hidden from the user, who only interacts with the domain name. This structure of delegation is what enables a network built on numbers to be navigated using language.